let's discuss limiting reactant and percent yield. Up until now in this chapter, we have been dealing with problems where a stoichiometric amount of reactants have been given to us, or that in the problem itself, it is stated that one reactant is already in excess, so we could ignore it. And that makes the problem a little bit easier to solve, but in real life, we don't have that luxury. In real life, we have to figure out what is going to limit the reaction. Oftentimes in a chemical reaction, one reactant will run out first. That reactant is called the limiting reactant. It is the reactant that will dictate, that will determine the amount of product you get at the end. And then one or more of the other reactants will be left behind, will be what we call in excess, will be left over. To understand this on a more intuitive basis, let's go back to our brownie example. Remember the recipe for a brownie that we talked about is that for every box of brownie mix, you need 2 eggs in order to get 1 tray of brownie. So that's the recipe, right? Say for example, when you go into your pantry, you found that you have already 2 boxes of the brownie mix and a full dozen of eggs, so 12 eggs. So the analogy here is using the original recipe, how many trays of brownie can you make? So we can do this kind of visually. Remember that for every brown box, you need 2 eggs, right? So 2 eggs are used. So that will give us 1 tray. Now we have a second box, so let's do that. And 2 more eggs, but that will give us 2 trays. So that's our answer, right? Which one of this is our limiting reagent? Which one ran out first? It's the brownie mix boxes, right? So we use all that up, whereas we have eggs left over. So from here, we can answer some questions. First question is, how many trays of brownies can we make maximum? In this case, the answer is 2, right? So 1 and 2. Another question we can ask is, what is the reagent in excess and how much of it is in excess? Well, we can see that the eggs are in excess, and there are 12 eggs in the beginning, and we use 4, so 12 minus 4 is 8. 8 eggs are left in excess. So we kind of did that on an intuitive level. Well, now in chemistry, it gets more complicated than this. So we need a more systematic way of approaching this problem. So I will teach you one way that I like to do it. And this way is to theoretically calculate what is the maximum amount of product you will get based on the reactant you have. And you're calculating it on one reactant at a time. So for example, I know that because there's a 1-to-1 relationship between my box of brownie mix versus 1 tray of brownies, I know that if I have 2 boxes of brownie mix, I can make 2 trays of brownies. Okay, so that's one scenario. The second scenario is to deal with my eggs only. In this case, I have 12 eggs. If I have 12 eggs and I ignore the amount of brownie mix I have, how many trays of brownies can I make? 12 eggs can give you 6 trays. In one case, if I had an unlimited amount of eggs and only 2 boxes of brownie mix, I can make 2 trays. In another scenario, if I had an unlimited amount of the brownie box and only 12 eggs, I can make 6 trays of brownies. So there's 2 worlds we're talking about here, right? Well, which one is smaller? Which one is limiting the amount you can make? It's the 2 trays scenario, right? So that's why in this case, the brownie mix is your limiting reagent. It limits how much maximum amount of products you can make. This question reads, how many moles of HCl can be produced by reacting 4.0 moles of H2 and 3.5 moles of Cl2? Which is the limiting reactant and which is in excess and how much is left? The balanced chemical equation is also given to us. Now, let's solve it on a more systematic manner. Remember, to know which one is your limiting, we just start with each reactant and going forward to calculate how much of the product we are making. So let's tackle one at a time. Start with H2. We have 4 moles of H2. So to calculate how many moles of HCl or how many amount of HCl that we produce, we need to have the mole ratio between H2 and HCl. The calculation is set up properly, giving us cancellation of moles of H2 and ending with units of mole of HCl. Okay, so that's scenario 1. Now let's go to scenario 2, where we start out with 3.5 moles of Cl2. Again, to convert moles of Cl2 to moles of HCl, we would need the mole ratio. Doing our calculation, we have concluded that we can create 7.0 moles of HCl. So between these two scenarios, which one will limit the amount of product you will have? It's the second one, right? 3.5 Cl2 will only give you 7 moles of HCl, not 8 moles of HCl. So Cl2 is your limiting reactant, and H2 will be your reactant that is in excess. And the last part of this question is how much is left over of the reactant in excess. So how much of H2 is left over? Okay, and to solve this, I need some more space, so I'm going to erase. Okay, so we need to know how much H2 is in excess. So that means we need to calculate how much H2 reacted, right? The difference between the amount that reacted and the original amount would be the amount that you have left over. That makes sense, right? So how much has reacted? How do we calculate that? Since we just figured out that chlorine is our limiting reactant, we can use that knowledge to figure out how much it reacted with H2, because they too have a mole-to-mole relationship, right? So let's do that. Again, we start out with 3.5 moles of chlorine. But now, instead of calculating how much HCl we created, we have to calculate how much it reacts with H2. So what's the relationship between hydrogen gas and chlorine gas? It's a 1-to-1 relationship. Doing our calculations here, we can see that you have used up 3.5 moles of hydrogen gas, right? So that calculation tells us how much was used. So the question is, how much remains? Well, what's left over? So to figure out what's left over, we just take what was the original amount minus what is the amount that was used. So 4.0 in this case minus 3.5, which comes out to be 0.5 moles left over. All right, so that's how you solve these kind of problems. All right, let's do another example. In this problem, it says that there is a reaction between magnesium metal and oxygen, and it is a two-part problem. Calculate the mass of magnesium oxide that can be produced if 2.4 grams of magnesium reacts with 10.0 grams of oxygen gas, right? So in a problem like this, where it doesn't give us a balanced chemical equation, we have to come up with it ourselves. So in this problem, it already gave us what reactants we were dealing with and what product we were making. All we need to do now is to balance this chemical equation. Looking at this, we realize that it is not yet balanced. So how do we balance this? Adding coefficients would balance the chemical equation. And double check if that's correct. Yes, and yes. So that's now a balanced chemical equation. Again, you cannot do stoichiometry if you do not have a balanced chemical equation, because the mole ratio is all based on the coefficients. So if you don't have the correct coefficients, then there is no mole ratio. You can't do stoichiometry. All right, so let's go back to the problem. It's asking us to figure out how much mass is going to be created when these two things react with each other. So let's go through our systematic method of calculating the hypothetical masses of the products that we will get based on two scenarios. The first scenario is looking only at the mass of magnesium. The second scenario, looking at the mass of only the oxygen. So how are we going to calculate the mass of magnesium oxide, the product that we can make? Given that we start out with 2.40 grams of magnesium, this sounds like a problem we did in the previous lecture, because you need to go from grams of something to grams of something else, right? The mantra of grams to moles to grams, right? So let's do that. From grams of magnesium, you need to go to moles of magnesium. And how do we go to moles of magnesium? Using the molar mass of magnesium. That's correct. All right, we just did from grams to moles. Now we need to go from moles of one thing to moles of another thing using the mole ratio. Right? So the mole ratio is for every 2 moles of magnesium oxide, you need 2 moles of magnesium. Again, cancel those units so we are taking care of them one at a time. And the last step, now that we have moles of magnesium, we need to go to grams of magnesium using its, again, molar mass. Before we punch these numbers in our calculator, notice that you can simplify your life a little bit by noticing that the 2 on the top and the 2 on the bottom here, they can cancel each other out, right? So that's one less step for you to input in your calculator. 2 divided by 2 is just 1, so they just kind of go away. So then put this into your calculator, 2.40 times 40.31 divided by 24.31. What do we get? We get 3.98 grams of magnesium oxide. All right, so that's scenario 1. Now let's go to scenario 2, where we base our calculations again on the oxygen only. So we have 10.0 grams of oxygen. Based on our oxygens, the grams of oxygens, we need to go grams of magnesium oxide. So therefore, grams to moles to gram. I'm going to go fast this time. All right, so there you have it. At the end, we calculated to be 25.2 grams of magnesium oxide. All right, so from those two hypothetical product calculations, what do you know would be your limiting? Which one is a smaller amount? 3.98. So your amount of product you are making is limited by what? By magnesium. That's correct. And what's in excess would be oxygen. So your final answer in this case, since it's asking you for the mass of magnesium oxide that you can make, your final answer is 3.98 grams of magnesium oxide. All right, let's take a pause here. I want to take this moment to clarify something here. Notice that in this example, I calculated grams of my product and compared it in 2 scenarios, whereas in the previous example, I only calculated to the moles of the product and then compared the 2 scenarios to figure out which is my limiting reagent. Well, it turns out both methods are okay as long as you calculate the amount of products you have, whether that amount is in units of moles or in units of grams. So either calculation is okay, but you want to be strategic about it. In the previous example, it didn't ask me for the mass of the products that I will make, so I can just stop at moles, right? So it saves me one extra step. But in this case, the question itself is asking me for the mass, so might as well, we should calculate the mass of both scenarios in order to compare them and figure out what is the limiting reagent. All right, hopefully that clarifies that point out for you, and so let's continue back with the lesson. All right, let's go to part B. Part B is asking us to determine the amount of excess reactant. Again, we already know which one is your excess reactant. It is the oxygen. So we need to know how much oxygen was used. Again, to find out how many oxygen we used, we will start with how much magnesium we reacted. This time though, instead of going to all the way to relationship with magnesium oxide, you need to go to amount of oxygen. So the mole ratio of oxygen to magnesium is a 2-to-1 relationship. Okay, so now we have moles of oxygen. We need to know then what is the mass of oxygen that was used. So using molar mass of oxygen. All right, so our calculation says we have used 1.58 grams of oxygen. Okay, to figure out what was left over, then we just start out with what was initial minus with what is used. So that's 10.0 grams minus 1.58 grams, so giving us 8.42 grams left over. Now, if we care about sig figs, we can't really report to the hundreds, since our least precise figure was only to the 10th in one of the numbers. So the answer is 8.4 grams of oxygen left over in excess. All right, our last concept in this section is about the percent yield. So the amount of product that we've been calculating thus far is what we call the theoretical yield, the maximum amount of yield, the best case scenario, the perfect case, where everything that you reacted 100% becomes your product. But of course, in life, it is often never perfect. We often come up short, a number that is less than a theoretical yield. We call this the actual yield. It's important to know how off you are. So using your actual yield and your theoretical yield, we can calculate what is known as the percent yield. And so this number, the percent yield, is just a ratio between your actual yield and your theoretical yield. It's a percentage, so multiply by 100. This number is quite important. For example, in organic chemistry, when you make drugs, for example, there are many steps, and you want to have a very high percent yield in these reactions, because the lower percent yield means that you are losing your reagent somehow. It's not going to its maximum capacity. And as you may know, if you're just adding reactants into a reaction and it's not being used to its full potential, then it's basically wasting that reactant. A waste of reactant translates to a waste of money, so lower profits. So this is hugely important in the pharmaceutical industry, for example, or even in the lab, right? We do not want to create unnecessary waste. So we want to have a high percent yield when we do a reaction. So to apply this concept, let's go back to the problem that we just did. We just calculated on that problem that our theoretical yield is 3.98 grams of magnesium oxide. Now, when we actually do the experiment, you may find that you only got back 2.85 grams of magnesium oxide. Then how would you calculate your percent yield? Right? So just the calculation would be set up as actual yield over theoretical yield times 100, which in this case is 2.85 grams divided by 3.98 grams times 100. Remember, the grams goes away, and your answer comes out to be 71.6%. So either in this class or in your future chemistry class, knowing how to do limiting reactant and calculating percent yield will be very important when you go into your labs. And of course, there's a lot of math in this section, and the best way to improve your skills in these is what? To do a lot of practice problems.